Topic 8's Lesson 4 is all about applying where and when we might actually see quadratics to model real-world situations. If you're a physics person, you may have heard of our vertical motion model, that is negative 16t squared. This has to do with our gravity's pull onto Earth, and that will be constant. This will always be our a value. VO times t, or v sub o, means our initial velocity, okay, what we're starting at, what we throw something into the air at, what the rate is. And then h of o is our initial height, where we throw it from. Or for example, with this diver, so the diver is going to jump off the board, and we want to make a function that models his height after t seconds. We use t in these equations because t is for time. H is for height. Let's look at where the diver is starting. He's starting 30 feet up into the air. So we would say our equation for his height at any time t, that means h of t, is the negative 16t squared always stays. Just take that as the gravity experts from the history in our past. They figured that out for us. We'll leave the middle for just a second, but the initial height of our diver, h of o, is 30 feet. That's how tall he is and high he is into the air when he dives. The last piece that we need is his initial velocity, at what rate he jumped off the board. And it tells us his initial vertical velocity is 16 feet per second. So this time we actually have two 16s in our equation, and that's all they need. For part B, it says how many feet above the platform will he be at the highest point? Well, there's our point on our picture. That always helps. That would be what we call our vertex. We're going to use that same idea for finding the vertex as we did in the last section, where we're going to use our negative b over 2a equation. So the opposite of our b over 2 divided by the a value. Now, if we think about this, if you don't want to multiply, the negative 16s would reduce and we'd have 1/2. So that would tell us that our axis of symmetry is at 1/2 in a half a second. So it only takes a half a second for him to peak in the air. But to find the actual height that he's at, we're going to have to plug that 1/2 into our equation, because that will give us our height. And by doing so, we could write it out here. We have 1/2 squared plus 16 times 1/2 and plus 30. This will actually give us 34. So our vertex up here is 1/2 comma 34. And since t is the x value, we kind of note that because this is in the spot where the x would be. The time is a half a second, and his maximum height is 34 feet. Now, I'm not going to solve all of the try it to, but they're just changing a few pieces of your original equation. What if he's diving from a 20-foot platform? Well, that would change his initial height, and his initial velocity, the speed at which he jumps off the board, if you will, would be 8. And again, remember this negative 16t squared stays the same when you're talking about dropping objects or falling objects. So you would use this equation now and do the same process of finding the axis of symmetry and the highest point with the vertex. One other thing we can talk about is when you have a set of data that you collect, and it looks like, if you plot it, that it kind of looks like a parabola, it's important that we can find how far off our real data is from a parabola that goes and fits closely to that parabola. So let's look here. We have a price of a ticket and how much they're going to increase the price by each year here. So it's probably based on our inflation. Then they say how much money the place makes, what they're actually making. In this first graph, they would ask you to plot all of the points and see where they lie and what shape it makes to see if a quadratic will actually model this data. So by a quick plot of our x's being the x values and our revenue being the y values on this graph, we see that, yeah, it kind of looks like it might be a quadratic. Now, think about that. If they raise the price too much each year, people will stop possibly buying it, and it could reduce your profit. They're going to tell you that an equation that they're using, the director is using this equation to estimate their profits. They found that that kind of fits this curve. So to find the predicted revenue, that means, say you want to go to the 5th price increase, you could use this equation to predict it. So for this predicted revenue, you're going to plug in every x value into this equation. If I put 0 in for x, we know these first two will go away. I get 750. If I put 1 into this equation, and again, you'll have to take my word for it, I'm not going to show these steps, but if I put a 1 into there, I would get 833. And if I put 2, and so on. So again, I am plugging this x value into this predicted model. It's a close estimate. It's not exactly what they earn. So we can tell that these numbers are all very close. And I'll finish here. They're all just really roughly estimated. That's why this parabola is his guess. He doesn't want to have to, he can't predict the future. So what we're going to look at is what's called a residual. That is what you got actually from raising the ticket price to what your equation predicted you would get. So this is the actual formula, or the real formula. Take your actual amount. We earned $745, but our parabola predicted that we were going to earn 750. Now I know that feels funny because it feels like your first number is smaller, but our residual is a -5. It means our parabola kind of overestimated what we were going to have. Or if I did 846 minus the 833, I would find that my residual is 13. So it had underestimated what we were going to make. We plot our residuals on this graph. So at 1, my graph was off by a -5. And at 2, my graph was off by 13. By plotting the residuals, and let me finish this real quick here for us. So I plotted all the differences in what I actually did and what my data projected. What we know when they ask how well does this function represent the actual revenue data, we can tell that it's a good function. Now we kind of saw that this was a pretty good parabola, not too bad. And we could actually graph this parabola. Say you had some digital abilities to plot those points on Desmos and the parabola, you would see they fit pretty darn good. Well, if we don't have that option to plot both of them, when we plot the residuals, having residuals that kind of bounce back and forth on the both positive and negative of the axis means that we had a good representation. So it's we could say it is a good representation. So that means the producer should use this model to predict his revenue. Even though it's not exactly on, those residuals being split up and down amongst the x-axis, some positive, some negative, would be a good fit for that equation. All right, lastly, let's say you have a director and they just kind of guessed this equation, like someone said, oh, it's some mathematician did it. What if you wanted to use these actual data points to make a quadratic? We have the ability to make a regression equation. So what you would do is you'd go onto Desmos and you would type in all your actual data on Desmos. You would take that data in a circle and go to Desmos and create that table. Then you'd have your X for your how many times you changed or what your ticket price went up by, and then your revenue. When you get that data entered into your table, then you're going to say, well, we think it's a quadratic equation that models it. So you're going to make an equation that's y1, and again, this is all on Desmos, y1 tilde ax1 squared plus bx1 plus c. This tells Desmos to make a quadratic function using the x1s and y1s from this table that you already typed in to make your best fit equation. And from there, it really is just Desmos doing the work for you. So you would find that they would give you their values, and your equation would be y equals -8 x squared plus 95.2x plus 749.8. Again, they give you all those numbers. So I would recommend that you go try on Desmos to type in your table from example 3. Use this equation right here, just as you see it. This one will always be the same, and that's because we think it's quadratic, and it will spit out that answer for you. So I've switched over to my Desmos screen just to give you one better example, and watch me. I would add the item of a table, and I'm going to enter all of those numbers from my data table on example 3. So give me just a second to do that here. So once I have this data, if you ever want to see it, you can click this little zoom fit button. And there we see it's kind of a parabola, and we want to make them create an equation for us. So we type our y1, and the little tilde buttons is the shift with the far left button by the 1. And then we type ax1 squared plus bx plus c. And when we hit enter, oh, I messed up something. I forgot my 1 here. It now creates our equation. So there's the -8, there's the 95.2, and there's the 749.8. And they're saying that is our best way to predict the equation, or the revenue you can make off that equation. Now, if you wanted to know, say on the 5th price increase, what the value would be, you could go and plug in your 5 into this equation, and it would tell you how much you would make after the 5th price increase.